This week we continue our discussion of logistic regression. In the previous video, we worked with the home equity data. This week we're looking at the diabetes data. So let me show you the variables and give a little explanation here. We're interested in whether or not somebody is diagnosed with diabetes or not, where 1 means yes, they were diagnosed with it. The potential predictors we have are age, blood pressure, cholesterol, stabilized glucose, weight, and gender. I will run this logistic code and include a scoring statement so that SAS will find my predictions for me, but I will show you in detail the work that's going on behind the scenes to make those predictions. I've already run this code, so I'm going to switch over to the results now. The table that I'm most interested in for writing my equation is the analysis of maximum likelihood estimates table. Let's go ahead and take a look at the other results that we have. We have only a couple of steps that SAS had to run to converge upon our model. We see our p-values meet our required level there. We have our odds ratio estimates. We have percent concordant and C-statistic look very good. Look at this ROC curve. This is a good curve. And I think I skipped over something. Yes, my model fit statistics. These intercept and covariate numbers are less than intercept only. And our testing global null hypothesis p-values are less than 0.05. So we are going to continue now with this model, which has only 2 predictors. We will take those and write our equation. And remember, in logistic regression, we say L equals, not Y equals. I have my intercept, I have my estimate for age, and my estimate for stabilized glucose. And now I'm ready to make predictions. My first question is, what is the probability that a 60-year-old man with a stabilized glucose level of 150 will be diagnosed with diabetes? Well, the fact that he's a man is of no consequence here. Gender did not remain in the model. Only age and stabilized glucose did. I'll plug 60 in for age and 150 in for stabilized glucose. So that's what I've done here below. And I will compute that in Excel in just a moment, but that value is a logit. It's not the probability. So I'll have to do an extra step. Now, how are these two related? Well, my probability is found by exponentiating the logit and dividing by 1 plus e to the logit. So I'll do that in Excel as well. And then in a little bit, we'll talk about interpreting our coefficients. So let me go ahead and move to Excel. So here I've got my values for the intercept, the age, the stabilized glucose. I'm going to be plugging in a 60 and 150. And what we have here in this column is the result of multiplying my coefficients by my values. And then when I total these, I get my logit. And I'll clear this value out and show you the computation for finding the probability from the logit. In Excel, E is EXP. So we will exponentiate our logit, and then we will divide by 1 plus e to the logit. And that gives us a probability. So this person who is 60 years old and has a stabilized glucose level of 150 has a 39% chance of being diagnosed with diabetes. So this is the type of work that goes on behind the scenes in SAS. SAS is multiplying these together, adding them up, converting to a probability. Now let's look in that scored data set that I called Predict Diabetes. And I'll scroll way over to the right. And this P1 column will contain all those probabilities that I just was computing for that particular observation of a 60-year-old man. P_1 is the probability of getting the diagnosis. And then P_0 is the probability of not getting the diagnosis. So these two values should add up to 1 for every observation here. When the probability is 0.5 or greater, then over here in this column where we have I_diagnosis, we'll put a 1. Now for all these that we see at the top of our list, the probability is less than 0.5, so we have a 0 in that column. We scroll down and find a higher probability. Here's an observation with an 84% chance of being diagnosed. That's greater than 0.5, so we'll put a 1 in this column. And then those will be compared against the original values in the diabetes data set for the diagnosis. And the more these match, the better our model is. Now, let me scroll back over, if I can, just a moment, please, and talk for a moment about these two columns. Actually, not those two columns, but any two observations compared against each other, and talk about percent concordant. So these two observations right here, where we have a 1 and a 0, just a reminder of percent concordant, what we will do is take a pair where someone does have the diagnosis and someone doesn't. And then we compare the probabilities. As long as the probability that the person who had the diagnosis is in fact greater than the probability of the person who didn't have the diagnosis, then we have what's called a concordant pair. All right, so let me review for a moment. Going back to our code, we will include a score statement in our logistic code to have SAS find our probabilities for us. In that data set, we will end up with 4 additional columns from our original data set. The probability that we do get the diagnosis, the probability that we don't. When that probability is 0.5 or greater, we'll get a 1 in the I diagnosis column. When it's less than 0.5, we get a 0. Now let's talk about interpreting. How do we interpret what we get? Well, instead of using the analysis of maximum likelihood estimate coefficients, instead of using these numbers, we'll actually use the odds ratio estimates. Okay, so let me go back to the results and show you that's a different table. Now this example is interesting in that my estimates up above for age and stabilized glucose were very close to each other, so my odds ratio estimates are basically the same. When my odds ratio point estimate is greater than 1, then as the variable increases, my likelihood of the response will increase as well. If this estimate was less than 1, then my probability would decrease as the variable increases. So let's go back to that Word document and talk about this particular value. We would say as our interpretation that with each additional year in age, a person is 1.037 times more likely to be diagnosed with diabetes holding all other factors constant. Okay, and just one more comment about these probabilities. These probabilities will also help us to group our observations, if we wanted to, into people highly likely to get the diagnosis, those who aren't very likely at all, and those with a moderate chance. We could just specify ranges for our probabilities if we wanted to do that. So having these numbers rather than just a 1 and a 0 is very helpful, but you need to know the relationship here as well, which is using 0.5 as a cutoff. 0.5 or greater gives us a 1, less than 0.5 gives us a 0. And that concludes this video on logistic regression.